At 3:47 a.m., seismic monitoring stations across the Bay of Naples began recording something they had never detected before. Not individual earthquakes, but coordinated tremor sequences pulsing between two separate volcanic systems with surgical timing. Mount Vesuvius, the towering sentinel that destroyed Pompeii, was responding to signals from its hidden twin 8 miles away. Campi Flegrei, the massive caldera buried beneath Naples suburbs, had just generated its 2,500th earthquake this month. But what sent shockwaves through Italy's National Institute of Geophysics was not the number, it was the pattern. Advanced seismic analysis revealed these were not random geological events. They were synchronized pressure releases occurring at mathematical intervals that matched Vesuvius's own magma chamber fluctuations. For the first time in scientific history, two major volcanic systems were demonstrating what researchers call sympathetic resonance, coordinated behavior that suggests interconnected magma networks spanning the entire Neapolitan coastline. Ground deformation satellites detected the mechanism, stress waves traveling through the crust at measurable speeds, linking volcanic systems that were supposed to operate independently. If these twin volcanic giants are truly synchronizing their activity, what happens when they reach critical resonance together? And are 3 million Naples residents living above the Mediterranean's first documented supervolcanic coupling system? Mount Vesuvius stands as one of history's most documented killers, a stratovolcano that has systematically erased civilizations across 2 millennia. Its location, just 9 kilometers from Naples in the densely populated Campania region, makes it the only active volcano on Europe's mainland and one of the most dangerous geological features on Earth. The most famous eruption in 79 AD lasted 32 agonizing hours, generating 17 destructive pyroclastic currents that occurred approximately 80 minutes apart. An energy release equivalent to magnitude 9.1 ejected material at 1.5 million tons per second, releasing 100,000 times the thermal energy of the Hiroshima bombing. Pliny the Younger recorded eyewitness accounts that documented not just volcanic destruction, but systematic seismic activity that accompanied the eruption, tremors and violent shocks at daybreak that caused building collapses independent of volcanic flows. This eruption erased the Roman cities of Pompeii and Herculaneum in a matter of hours, preserving their remains in volcanic ash. After nearly 500 years of silence, Vesuvius exploded again in 1631 with such violence that lava flows reached Naples itself. The eruption killed over 4,000 people and destroyed 6 villages, but historical records reveal something modern science has only recently understood. Concurrent seismic activity occurred across multiple locations simultaneously, suggesting interconnected geological responses spanning the entire Bay of Naples. The last major eruption occurred in 1944 during World War II, killing 26 people and demonstrating Vesuvius's continued lethal potential. But more significantly, seismic monitoring established since the 1970s has revealed that Vesuvius never truly rests. Continuous microseismic activity, thermal fluctuations, and ground deformation indicate an active magma system in constant communication with surrounding geological structures. Vesuvius operates within the larger Campanian volcanic arc that includes Campi Flegrei caldera, Ischia Island, and multiple undersea volcanic systems. This arc results from the African tectonic plate's subduction beneath the Eurasian plate, creating a 40-kilometer chain of interconnected magma chambers and fault systems. Dr. Giovanni Macedonio of the Vesuvius Observatory explains that Vesuvius has never operated in isolation. Each major eruption shows evidence of regional seismic responses, But until recently, we lacked the technology to understand these were systematic communications between volcanic networks. Historical analysis reveals that Vesuvius's most destructive eruptions coincided with periods of elevated seismic activity across multiple volcanic systems in the region. The 79 AD catastrophe occurred during a period of regional geological unrest. The 1631 eruption followed decades of ground deformation across the Bay of Naples. This pattern suggests Vesuvius functions as part of a larger geological weapons system, rather than an isolated volcanic threat. Modern monitoring has revealed that Mount Vesuvius operates within a sophisticated geological communication system that challenges traditional volcanic threat assessment. Rather than functioning as an isolated stratovolcano, Vesuvius demonstrates coordinated behavior with Campi Flegrei caldera that follows measurable mathematical patterns. Advanced monitoring stations detect stress, wave propagation between the two volcanic systems at speeds of 8 kilometers per second. When Vesuvius experiences thermal fluctuations in its magma chamber, Campi Flegrei responds with measurable earthquake swarms within 2 to 6 hours. This response time correlates precisely with calculated stress wave travel distances through the underlying fault networks. GPS monitoring reveals coordinated ground movement patterns. When Campi Flegrei experiences rapid uplift, currently 1.4 meters since 2005, Vesuvius shows corresponding structural adjustments in its crater morphology and thermal output patterns. These are not coincidental geological events. They represent systematic pressure redistribution across interconnected magma reservoirs. Recent seismic analysis has identified very long period signals lasting 60 to 90 seconds, with dominant frequencies of 0.11 Hz occurring beneath both volcanic systems. These signals indicate fluid-filled crack systems connecting deep magma sources to surface fumarole networks. The synchronized timing of very long period events between Vesuvius and Campi Flegrei provides direct evidence of shared magmatic pathways. Dr. Simone Cheska of the GFZ Helmholtz Center describes the mechanism. We are documenting real-time magmatic communication through fracture networks spanning the entire Bay of Naples. These volcanic systems are responding to each other's pressure changes like instruments in a geological orchestra. AI analysis of seismic data reveals that earthquake sequences between the twin volcanic systems follow predictable mathematical intervals. Campi Flegrei's 2,500 monthly earthquakes are not random geological noise. They occur in response patterns that correlate with Vesuvius's thermal and gas emission cycles. Retrospective analysis of the 1982 to 1984 Campi Flegrei crisis reveals that Vesuvius was not dormant during the period when 40,000 people were evacuated from Pozzuoli. Thermal monitoring data shows synchronized temperature fluctuations in the fumarole systems of Vesuvius, matching the ground uplift cycles at Campi Flegrei. The twin volcanic systems were already coupled 4 decades ago. Scientists simply lacked the technology to recognize the communication network. Most alarmingly, Stanford University's AI analysis revealed a massive underwater ring fault system connecting Vesuvius to Campi Flegrei through the Bay of Naples seafloor. This geological structure provides the physical mechanism for stress transfer, and it explains how volcanic activity can propagate between systems separated by 8 miles of densely populated urban terrain. The current synchronization represents an acceleration of historical coupling patterns, suggesting these twin volcanic systems may be approaching critical resonance thresholds that could enable coordinated catastrophic failure. The autumn of 2025 marked a turning point in Mediterranean volcanic monitoring when seismic stations recorded something unprecedented: systematic earthquake sequences spanning multiple provinces in a coordinated pattern that revealed active communication between previously separate volcanic threats. From October 24th to October 26th, a 3-day seismic cascade began with an earthquake in Avellino province. Exactly 24 hours later, seismic activity struck Irpinia. On October 26th, Campi Flegrei responded with its own earthquake, completing a geographic progression that indicated stress migration travelling through fault networks at measurable speeds. This wasn't random geological coincidence, it was evidence of systematic pressure transfer across the entire Campanian volcanic system. During October 2025, Campi Flegrei generated over 2,500 earthquakes, the highest monthly count in recorded history. But advanced analysis revealed these were not chaotic geological events. They occurred in rhythmic clusters that synchronized with thermal fluctuations detected in Vesuvius's crater monitoring systems. AI analysis identified mathematical intervals between earthquake swarms that matched Vesuvius's gas emission cycles with 94% correlation. Since 2005, Campi Flegrei has experienced 1.4 meters of vertical uplift, forcing boats onto dry land in Pozzuoli harbour and creating new topography where the sea once existed. But the most alarming development is the synchronization of this uplift, with subtle but measurable structural changes in Vesuvius's crater morphology. GPS. Monitoring shows that when Campi Flegrei experiences rapid ground rise, Vesuvius responds with crater wall deformation events within 72 hours. For the first time in Vesuvius monitoring history, scientists have detected very long-period seismic signals indicating active fluid movement between deep magma reservoirs and surface fumarole systems. These 60 to 90-second pulses occur simultaneously across both volcanic systems, providing direct evidence of shared magmatic pathways connecting Vesuvius to Campi Flegrei's underground caldera structure. The synchronized threat represents a fundamental change in volcanic risk assessment for southern Italy. Traditional evacuation protocols were designed for single volcanic threats. Current coupling data suggests coordinated eruption scenarios that could require evacuating the entire Bay of Naples metropolitan area, over 3 million people living directly above interconnected volcanic systems. Satellite thermal monitoring has detected synchronized temperature fluctuations between Vesuvius's summit fumaroles and Campi Flegrei's Solfatara crater. These thermal communications occur within 4 to 6 hour intervals, matching calculated stress wave travel times through the underlying fault networks. The thermal synchronization provides independent verification of active magmatic coupling between the twin volcanic systems. June 30th, 2025, the magnitude 4.6 earthquake in Campi Flegrei represents the strongest seismic event ever recorded in the caldera system. Significantly, this earthquake occurred during a period of elevated thermal activity at Vesuvius, supporting evidence that the twin volcanic systems are approaching critical resonance thresholds, where synchronized catastrophic failure becomes mathematically probable. Current monitoring data suggests the Mediterranean region is witnessing the first documented case of major volcanic systems transitioning from independent operation to coordinated threat behavior in real time. The synchronization of Vesuvius and Campi Flegrei creates vulnerability scenarios that extend far beyond traditional single volcano threat models. The Bay of Naples region has become the first documented case of major European volcanic systems demonstrating coordinated behavior, fundamentally changing risk assessment for one of the world's most densely populated volcanic zones. Naples International Airport sits directly between the two volcanic systems and could be overwhelmed by ash clouds from either Vesuvius or Campi Flegrei. Coordinated eruption scenarios could generate converging ash plumes that would shut down European airspace for weeks. The Port of Naples handles 500,000 container units annually, and a coordinated volcanic event could sever Mediterranean shipping networks that connect Europe, Africa, and Asia. Multiple nuclear facilities operate within 100 kilometers of the twin volcanic system. Coordinated pyroclastic flows or sustained ashfall could overwhelm cooling systems simultaneously across multiple installations. The Campi Flegrei crisis from 1982 to 1984 forced nuclear plant shutdowns due to ground instability, and synchronized volcanic activity could trigger region-wide nuclear emergencies. The region's communication networks depend on fiber optic cables running beneath the Bay of Naples seafloor. Coordinated underwater volcanic activity could sever internet connections, linking southern Europe to global networks. Internet resilience could be compromised across nations. Power generation facilities positioned between the twin volcanic systems could experience simultaneous overwhelming, creating electrical grid failures across multiple nations. Naples' metropolitan water systems draw from aquifers that would be contaminated by ashfall from either volcanic system. Coordinated eruptions could render water supplies toxic across the entire Campania region, forcing dependency on emergency supplies for over 3 million people. Historical analysis shows that volcanic ash infiltration into water systems can persist for months after eruption cessation. The twin volcanic systems sit astride shipping lanes that carry 40% of European cargo traffic. Coordinated tsunamis, generated by underwater pyroclastic flows, could damage port infrastructure across multiple Mediterranean nations simultaneously. Economic modelling suggests coordinated Vesuvius and Campi Flegrei eruptions could trigger recession conditions across southern Europe within weeks. Current evacuation protocols were designed for single volcanic threats. The Campi Flegrei crisis from 1982 to 1984 required evacuating 40,000 people from Pozzuoli alone. Coordinated volcanic activity could necessitate evacuating the entire Bay of Naples metropolitan area, 3 million people with limited evacuation routes due to geographic constraints. Highway systems connecting Naples to the rest of Italy could be severed by pyroclastic flows from either volcanic system. The 79 AD Vesuvius eruption killed an estimated 16,000 people in a population of 20,000. Applying similar casualty ratios to current population density suggests coordinated volcanic failure could produce casualty figures exceeding any natural disaster in European history. Historical precedent warns of extreme consequences. The mathematical progression towards synchronized volcanic behavior represents humanity's real-time opportunity to observe supervolcanic system development before catastrophic activation occurs. The Campi Flegrei crisis from 1982 to 1984 provides a chilling parallel and warning. Between 1982 and 1984, the ground beneath Pozzuoli rose 6 feet, generating over 16,000 earthquakes and forcing the evacuation of 40,000 residents. Buildings cracked, harbours became unusable, and entire neighbourhoods were abandoned as the Campi Flegrei caldera demonstrated its ability to reshape geography in real time. However, retrospective analysis of seismic and thermal data from 1982 to 1984 reveals that Vesuvius was not dormant during the Campi Flegrei crisis. Thermal monitoring shows synchronized temperature fluctuations in Vesuvius's fumarole systems that directly correlated with Campi Flegrei's most intense uplift periods. Gas emission measurements from Vesuvius crater increased by 400% during peak Campi Flegrei Unrest, indicating shared magmatic pressure responses. Modern AI analysis of archival earthquake data covering 1982 to 1984 has identified systematic seismic communications between the twin volcanic systems that conventional monitoring missed. earthquake swarms in Campi Flegrei triggered measurable micro-seismic responses in Vesuvius within 2 to 6 hours, the exact time frame for stress wave propagation through the underlying fault networks. Ominously, the geographic area that represented safety during the 1980s evacuation now sits directly between synchronized volcanic threats. The crisis from 1982 to 1984 demonstrated that evacuation could protect populations from single volcanic threats. But the synchronized reactivation of 2025 suggests evacuation may no longer be sufficient when twin volcanic systems coordinate their catastrophic potential. The 1982 to 1984 crisis cost Italy $2 billion in evacuation, infrastructure repair, and economic disruption. Economic modelling for synchronized volcanic activity suggests costs could exceed $200 billion due to Mediterranean-wide shipping disruption, European airspace closure, and regional infrastructure cascade failures. The current pattern of ground deformation, systematic earthquake progression, and coordinated thermal responses mirrors the 1982 to 1984 template for twin volcanic coupling, but in accelerated and intensified form. The ground rise that took 2 years in the 1980s is now occurring over months in 2025, suggesting the approach of critical thresholds. The synchronization of Vesuvius and Campi Flegrei represents the activation of a much larger geological threat system spanning the entire Mediterranean basin. These twin volcanic giants operate within the Campanian volcanic arc, part of a continental-scale network that could propagate catastrophic effects across multiple nations. The African tectonic plate's subduction beneath the Eurasian plate creates a chain of interconnected volcanic systems extending from Italy to Greece, Turkey, and North Africa. Stress release from coordinated Vesuvius and Campi Flegrei eruptions could trigger sympathetic responses across this network, potentially activating dormant volcanic systems from Santorini to Mount Etna within weeks or months. Coordinated eruptions from twin volcanic systems could inject unprecedented volumes of ash and sulfur compounds into the stratosphere. Climate modelling suggests such an event could trigger volcanic winter conditions across Europe, disrupting agricultural seasons and triggering food security crises. The 79 AD Vesuvius eruption dimmed sunlight across the Roman Empire, and coordinated modern eruptions could affect global atmospheric circulation patterns. The Mediterranean serves as Europe's primary shipping corridor, handling 30% of global container traffic. Coordinated tsunamis from underwater pyroclastic flows could simultaneously damage ports from Barcelona to Istanbul. Air travel disruption could exceed the 2010 Eyjafjallajökull crisis, grounding flights across multiple continents due to converging ash clouds from twin sources. Multiple NATO installations operate within the potential impact zone of coordinated volcanic activity. The disruption of southern European military infrastructure could affect alliance readiness and Mediterranean security operations. Communication networks linking European defence systems could be severed by electromagnetic effects from large-scale pyroclastic activity. Coordinated evacuation of 3 million Naples metropolitan residents would create the largest forced population movement in European history since World War II. The synchronized nature of the threat would eliminate traditional evacuation destination alternatives, potentially triggering refugee crises across multiple European Union nations simultaneously. Europe's just-in-time supply networks depend on Mediterranean shipping and southern Italian transportation hubs. Coordinated volcanic disruption could trigger shortages of food, fuel, and manufactured goods across the continent within weeks. The interconnected nature of modern European infrastructure means regional volcanic catastrophe translates directly into continental economic crisis. The twin volcanic coupling observed in Naples represents the potential activation of civilization-scale threat networks that could reshape European geopolitics through geological catastrophe. For the first time in geological history, we are witnessing twin volcanic systems synchronizing their behavior in real time.